We're back with a quick lecture that integrates some of the ANOVA review that we kind of have to do with what we've been discussing, and it sets up the big ANOVA lecture. Following up on the lesson from last lecture, lesson 1, that the general linear model is behind nearly all of our tricks, so everything is the same thing, we're going next lecture to scale up to higher dimensions to find that models with more predictors, or independent variables, are the same thing too. That is, ANOVA is regression. Now, not all regression is ANOVA, but all ANOVA is regression analysis. You heard that right, ANOVA is multiple regression. We will shortly see, in this and next lecture, how general linear models assume effects are additive. That is, as we add each predictor, it's assumed that the usefulness of each is usefulness in addition to what came before. Anything the new predictor explains that the old predictors already explained is not recognized or cared about, and anything that the new predictor, call it x3, explains that the old predictors x1 and x2 did not explain is credited to the new predictor, and the variation thus captured cannot then be attributed to any subsequent predictors, x4, x5, etc., that may explain the same thing but have come too late to the party to get credit. Putting this another way, that is a bit more technically accurate, regression analysis assesses in sequential order, i.e. additively, whether adding each new predictor, x2, x3, x4, reduces the sum of squared distances of the points from the regression line. If a new predictor's partial influence on the slope helps it to better model the scatter in y by reducing these residuals, these distances, then it is a statistically significant predictor. By some approaches, this is the only reason to keep a predictor in one's model, but this sparse and Spartan approach of saying don't come to the potluck unless you bring a unique dish doesn't actually make much sense when we consider what our model means. Sure, if we have IQ and GPA doing the same work, adding one after the other doesn't improve the model, and it messes up our diagnostics. But including only one suggests that the other is not important, which is empirically wrong, and prevents us from catching or modeling correctly the few present and future cases where the influence might only be captured in one measure. So someone who did not have a good day when they wrote their IQ test, or some powerfully intelligent person for whom school is torture. And this is epistemically wrong. So, regression is just additive. This means no accounting for synergy, or how predictor variables might influence other predictors? Well, no. We can add in clever combinations of predictor variables to see whether a predictor that is some combination of other predictors independently or additively decreases our prediction error. Regression lets us add whatever we want. Adding a new predictor that is a combination of other predictors is what we're doing when we test for interactions. This term, interaction, is what we call the trick or procedure when we are in the land or framework of ANOVA. Interactions, or interaction terms, can be placed into or added to regression models as easily as ANOVA models, because they're the same thing. But in regression land, we tend to call testing for interactions moderation analysis. But this lecture keeps it simple. Let's pick up where we left off with our nice simple model comparing U of T to Trent student performance, which I realized was a missed opportunity to show you how to do box plots in R, which is very simple. We put our y-axis variable first and communicate using the little wavy tilde line which independent variables we want to predict or describe this dependent variable with. We see the higher mean and the greater spread of U of T students in this graph. The correlation test told us that the student's university is associated with or explains some of their test score. The simple regression told us that including university as a variable reduces our error when we predict test score, and the t-test told us that our observed mean difference between the universities would be very surprising if there was not a difference between the groups we sampled. Of course, ANOVA is just our fancy way of running a t-test with more groups or more conditions in the grouping variable. So this command will just give us results that tell us what the t-test tells us in this case. Specifically, it tells us that the probability of obtaining our data if there were no actual group difference between U of T and Trent is 0.001621. Let's put this up here and run our little baby ANOVA, which unsurprisingly tells us that the probability of obtaining our data if there were no actual group difference between U of T and Trent is 0.00162. We can recall that the regression said the same thing and even gave us the same F statistic, the Fisher statistic, named for Ronald Fisher, that the ANOVA gives us. The regression, of course, gives us much more to work with, more information, and in a much more accessible form. Let's compare the regression output's residual standard error, which is the standard deviation of the misses, the prediction residuals. Compare that with how the same information is presented in the ANOVA table, which gives us the variance of the residuals. You can see that taking the root of the mean squared residuals, or mean squared error, gets us the residual standard error. The square root of 309.5 is 17.5926. I prefer the 17.59, the residual standard error, and I like to summarize it as how much we tend to be off by in our prediction. Okay, so ANOVA is regression. But the ANOVA table gives us different information than the regression output, and this is useful. If we're using different software like SPSS or SAS, it will usually by default give us an ANOVA table as supplementary output when we run a regression. So let's take a look at what it offers us, starting with this, which is the sum of squared error reduced by using the model, or put another way, the sum of squared residuals that the slopeless model had that ours does not. Or put another way, the error explained away or accounted for by including university in the model. Whether 3,116 is a nice number depends on the scale that we're measuring in and how much error we started out with, which would tell us how much we still have. So let's keep looking to contextualize this 3,116 number. Did university explain away a lot of error? This is the sum of squared error for the model. In other words, how much error was left after adding university to our model. Put another way, the sum of squared residuals is the regression model with a slope. And put another way that is actually novel here, our error when using the mean of each group to predict its members' scores. The mean of each group to predict its members' scores. So recall our Klingon versus human example where we saw how t-tests are just regressions with two outcome states. If Klingon predict 15, if human predict 3. This two-guess approach is compared in the t-test to guessing the mean of the outcome variable every time. Rather than having one mean to guess, the so-called grand mean, in this case the average across species, the model gives us two. We can guess the mean of humans for a human case and the mean of Klingons for a Klingon case. So, when we are using the U of T mean to guess U of T cases and the Trent mean to guess Trent cases, we have a sum of squared error of 127,192. That is apparently 3,116 squared error units better than we would be doing by guessing the grand or combined mean of both universities every time. Our error in that case, our error if we guessed the grand mean for every case, would be the total sum of squared error, also called the sum of squared error total. 127,192 plus 3,116 equals the total sum of squared error, which equals 130,308. In this case, the following descriptions are all equivalent. This is the sum of squared residuals of the slopeless regression model. This is the error when using only the mean of y for prediction, or this is the error when using the grand mean for prediction. Moving on to the mean squared error column, this tells us the variation in the grades accounted for specifically by our including university in the analysis, and the variation in grades we have not been able to account for, or explain, or eliminate, divided by the number of scores that were free to vary the degrees of freedom. The 413 students minus 2 for the fact that they come from 2 groups. It is the ratio of these two things, variance explained by the model, framed in purple, over variance left, unexplained by the model, framed in blue, that comprise the F value, the Fisher value, which is what we use to consult these sacred tables, and is the explained variance divided by the unexplained variance. The amount of squared error removed from the grand mean model by including the independent variable divided by the amount of squared error that remains. Said even another way, variation in y accounted for divided by variation in y not accounted for by the model. So far, we haven't actually dealt with an example that requires ANOVA, an example with more than 2 conditions or grouping variables. We're going to do that next lecture so that a one-way ANOVA, a two-way ANOVA, interactions, and ANCOVA can be covered in one large, well-visualized example that drives home the fact that they are all just examples of regression. Before we move on to that, a rather sizable task, let's review what prepared us for it. The general linear model, drawing the best straight line we can through the best data we can and assessing our errors, underlies everything that we're doing. That is even what we're doing with logistic regression, but since in that case we were doing so with dependent variables with non-normal error distributions, using a clever link function, the logit, to obtain linear values that form a boring straight line, but whose back-transformed probabilities make that pretty S, because we were doing that, we were, with log regression, using the generalized linear model. Much of advanced statistics is getting the general linear model to do things you wouldn't think you could do with a straight line. In visual terms, everything is just a test of whether and how much tilting the line at the mean of y and mean of x significantly reduces the squared distances between the line and our observed points. Here we have the U of T and Trent test scores analyses and what we could visualize as the regression analysis that is happening under the hood in R. We will next, technically, be doing higher dimensional modeling, and yet we will be testing / asking the exact same thing. Does this factor or variable add tilt or variation that can make use of that tilt to reduce error? Next lecture, we will go from a nice, simple 1x4 ANOVA to a 4x3x2 ANOVA, or ANCOVA, seeing visually how much richer our model gets as we add information and variability. Stay tuned.